Yeah. So let us continue the discussion on the Moore machine and the Mealy machine. We are studying sequential circuits, which means that the output of the system not only depends on the input at a point of time, but also on the state of the system at that point of time. So as let me quickly recall. So what we'll do today is that we will,
Excuse me, sir.
yeah, yes, tell.
Hello, sir.
Is
Am I
that,
audible?
yeah, you are audible. You are audible, tell. Am I audible?
Yes, sir.
Okay. Okay, okay. So can I continue? Am I audible? I hope I'm audible.
Yes, sir. You're
Yes.
audible.
Okay, okay, okay. All right. So a quick recall. You represent.
Hello,
Hello.
sir.
Huh.
Yes, sir. I had a question, sir. Will we have a test this Wednesday?
No, no. This Wednesday we are not having a test. I'll tell you what we'll do. We'll complete our discussion on the sequential circuits this week. Okay, and the next week we'll have a test whose syllabus would be logic minimization. That means the Carnot map and the Quinn McCluskey, as well as the sequential circuit design, which we'll
Right.
study this week.
Okay,
Next
sir.
week we'll adjust it. One more announcement. We are not having the lab also today. We are extending the lab assignment deadline till today evening. Many people have requested. We are extending it till today 5 o'clock. And we are not having today's lab. Tomorrow we'll upload an assignment on sequential circuits, for which again 1 week time will be there. 1 week time will be there for that. Okay,
Right.
so last lap continues till end of today's at till 5 o'clock today. All right,
Sir,
we'll extend the deadline in WECM.
sir. S- Hello, am I audible?
Yes, yes, you are audible.
So can you please give us the updates on the timetable that was supposed to be sent?
See, I'll tell you, the problem is I talked with the teachers, and none of them are sure that they can stick to that timetable. So they are telling that many of them had planned something, and there was some holidays in between, and all those things. So but what I could convince them is that they will give at least 1 week notice before conducting the test. So they said that
No, sir.
exact date. uh,
I'm talking about the SCLD timetable, about the tests and all.
Okay, so next week there'll be 2 more tests. Next week there will be a test next Wednesday, not this Wednesday, the next week's Wednesday. There will be the test, that will be the third test, and there will be one more test after the end of instruction. That means after we finish all the lecture classes, then there will be one more test. That's it.
And sir, what will be the syllabus and weightages of them?
The syllabus will be the interval between one test and the other test, next test.
So
Whatever
the
is taught.
last test is going to be the
The
interval
remaining
between the
part,
third test and the
remaining,
fourth test.
right, right.
Okay. And all of the tests are going to be having equal weightages.
All of the tests will have equal weightages, but we will have best 3 out of 4 tests.
Okay, sir. And one last thing, could you tell us about the distribution between the assignments and the tests?
See, that we are not decided fully. What I'll tell you honestly, what will happen is that we'll look at the marks distribution of the students that we get. We will try to be a little more lenient than the other semesters, but we have to stick to some basic grade distribution. So we'll look at the marks distribution of marks in each of the thing, and then we'll decide the weightage. But you don't worry. I mean, nobody. I mean, it will be good. So it will be better than other semesters. The grade distribution. So don't worry about that. Okay. The
Okay, sir.
weightage will
Thank you.
decide after looking at the marks.
Okay, sir.
Okay. All right. So this is a 6 tuple that characterizes a Mealy machine. You have a set of states. You have an initial state, which is kind of a reset state. Once you are back to the Q0 state, it's kind of the system is reset and starts operating. You have a set of input combinations, which we call the input alphabet. Input combinations may be just 0, 1, or some number of bits. So there is a combination of inputs that are possible. Delta is the combination, is the possible outputs that can happen. And you have a transition function which takes you from one state to another. So the next step is determined by the current state as well as the input. So Q cross sigma, which is why it's a millimachine. And you have an output function which also maps the states and input. Sorry, it's not it's millimachine because lambda is Q cross sigma to delta. Okay, so that's why it's a millimachine. So we have these combinations, and so now what we'll do today is that this is all fine. This is a formal theoretical description, but in practice, for a practitioner point of view, this entire millimachine or Moore machine or finite state machine, whatever you call it, is nothing but a piece of circuit. It's just some circuit. But since it is a sequential circuit, it has a special type of, it has a new type of element as compared to combinational circuits. It's a memory or a flip-flop, okay, which kind of represents a state. It kinds of holds information of which state the system is in. So because it is a sequential circuit, it has a flip-flop element. Now this can be several types of flip-flop. You have already seen the D flip-flop. And so D flip-flop, you get, as the clock comes, the input gets reflected in the output. So D goes to Q as the clock comes, as the rising edge or the falling edge of the clock. And you can have other type of memory elements. So you can visualize the D flip-flop as the following. The output Q, you can think of it as a which holds for certain amount of time, at least for one clock cycle it holds. And whenever a new input comes, a new D comes, it's kind of overrides this memory. If the input is 1, it's overwritten and the memory becomes, content of the memory becomes 1. When the input is 0, it becomes 0 at the clock. So you can think of this D flip-flop as a memory, which is overwritten at every clock cycle. So if it's overwritten by the same value, it stays the same. So it holds for certain amount of time. Also, since it is a synchronous circuit, all these changes happen only at the edge of the clock. So you also need an additional element for you have an additional element for a synchronous circuit. It's a clock at which all changes happen. Any state change happens. Okay, so now the thing is that we have talked about D flip-flop. There can be other type of flip-flops also. There can be SR flip-flops. There can be JK flip-flops. Sometimes those are more convenient. You can use them. If you use them, you have less circuitry. But the thing is that with the help of some combinational circuit elements, any flip-flop can be converted to any other flip-flop. So the operation of any flip-flop can be realized using any other flip-flop. So a D can be converted to SR, SR can be converted to JK, JK can be converted to, just by using some combinational circuits, they are equivalent if we use those combinational circuits. So to keep things simple, we'll go on with our discussion with D flip-flop, but maybe in the later part we'll do some design using other type of flip-flops also. So as a piece of circuit, you have some gates and you have these memory elements and you have a clock. So what we'll try to do today is we'll try to go through the following steps. First is we'll have a problem specification. What is the function of the circuit? Second is from the problem specification, we will try to represent it as a finite state machine. There can be other representations also possible. Finite state machine are not. There are something called algorithmic state machines, which are more useful for we will stick to for the moment to finite state machines. So the first step will be given a problem specification, convert it into a finite, represent it as a finite state machine. This will involve definition of the states. This will involve definition of the transition functions. This will involve definition of the outputs. Next step is that given a finite state machine, by the way, a finite state machine we'll see can, besides this formal definition, it can be represented in two useful ways. One is a state transition diagram where we have vertices and directed edges. One is a state transition diagram. Other is a state transition table, which we have also seen. So these are again two different ways of looking at the same thing. So the next step is that we will obtain the state transition diagram and the state transition table. Now the next step is that we will try to realize the state transition diagram and the state transition table. What is required? Now, two things are required for this. First thing is that you have to do something called a state assignment or a state encoding. What you do there is that you try to characterize a state by some encoding or some representation, usually a bit string, a k-bit string. Okay, so you have k-bit string, you can represent 2 to the power k states. This is the first part. Second part, you have to decide what type of memory element you will take. You will take a D flip-flop, you will take a SR flip-flop, or you will take a JK flip-flop. You have to decide which type of memory element you will take, which type of flip-flop you will take. And once these two are fixed, what is the state encoding and what is the flip-flop you will take, now the next step will be to design the combinatorial circuit. You remember in your Huffman machine representation or the simple Mir machine, Muli machine, there is something called a combinatorial cloud, and you have a primary input, you have a primary output, you have a second state input or excitation input and excitation output. And now the next step would be to design this combinatorial cloud, combinatorial circuit, which will satisfy the specific, which will meet the specification. That is one more step also left, which we'll do. You can actually do, just like you do in combinatorial circuits, you can do a minimization for sequential circuits also. You can reduce the states, you can reduce the combinatorial circuit. So we'll also go through those methodologies where you can reduce a sequential circuit to have the minimum. So let me these three steps that I talked about: specification to FSM, FSM to a realized or state assignment, and state assignment to combinatorial circuit design. These three steps will carry out. Yeah.
Sir, I'm changing the slides because we can't see
you
the
can't change the slides.
Yes, sir. It's still at melee machines are in finite.
Tuple. Yeah. Okay. Then I have to close and start. Then I have to close and start with. Is it changing now? Am I at D flip-flop?
No, sir, you are at million more machines. Now the screen is blank. Yes, yes. Now it is appearing.
Or there is a delay basically. Am I at millimachine example 1?
No, sir.
Just wait a bit.
Yes.
Yes, sir. Now it, yeah.
Okay. So let us quickly go to the, or let me go to the second example directly. All right. So so first example, finding out the 2's complement, that you have already done. Yeah, you know there are two states. Whenever you get the first one after the trailing zeros, you have a state transition and there are two states. Okay, now let us come to the second example. The specification is as follows. You have a three bit you have a 1-bit input. So if I draw the circuit, it's like an 1-bit input. Let me see if I can draw it. Okay, so the specification is as follows. You have an input X, a single bit input X, which comes only at the clock. And you have an output. So X can be 0 or 1. And the output Z can be A or B or C. So delta is A comma B comma C. So what you do is that I forgot the exact pattern. Okay, let's take any pattern. So if the input is this, so you get inputs like this 1 1 0 1 1 1 1 something, some input you get. Okay, so what we do is that whenever there is a sequence 0 1 0, you output A. Whenever there is a sequence, maybe an overlapping sequence 0 1 1, you output B. And whenever, let's say, there is a sequence 1 1 1, you output C. Okay, so the output would look like this. You have not seen the sequence yet, 0. You have not seen the sequence yet. Here it is A, and then it is 0, it is 0, and here it is B, and here it is C, and then you have C again here, you have C again here, you have C again here, you have C again here. Okay, so this is how you should behave, and this happens only at the clock. So you have to design a sequential circuit to do this. So let us formally look at the things. All right. So maybe I got this slightly wrong. Maybe I got this slightly wrong. Okay. So the actual specification is A is when you get 101, B is when you get 110, and C is any other case. So as I have told you, the first step will be to write down. Anyway, the first step will be to define the sigma and the delta. So sigma, as I have told, is 0 or 1, and delta is A or B or C. And now I have to define the state transition table, which, as you know, looks like this. You have the present state, and depending on different values of input, which can be either, because sigma is 0 or 1, our input is 0 or 1, you have the next state, and you also have the corresponding output. Okay, you also have the corresponding output, and you start with present state. Okay, all right. So can you tell me what can be the possible states here? What can be the possible states here? So as I have told you that what can be possible steps here without doing any minimization or anything. Without doing any minimization or anything. How many states do you need to characterize this?
4 states.
Why 4 states? Why can't we do with less number of states? Or why are you suggesting 4 steps? 4 states?
Because so that is what is there on the screen right now.
No, but okay, so I am asking you why it is there on the screen. Why do we have 4 states? Can you tell? Can you just looking at the specification?
Like, so there are ways one start state and then there
There
are,
is one start state. Very good. There is one start state. And why are there three states?
because you have got, you need three different like output things, well, not output exactly, input patterns, 101, 110 and everything else.
Yes. So can you tell me what are the physical meaning of these states? What means that if I am state Q1, what does it mean? What I have seen in the string so far, input string so far?
I have seen the last digit is a 1 if I'm
Yes.
on state Q1. For Q2, it means that the last two digits are 10.
Okay.
For state Q3, the last digits are ones only, like set of ones.
All right. So let me tell it is like this. So I start with Q0. Forget about this encoding. Don't bother about this encoding. So the message from here is the encoding can be entirely different from the physical meaning of the states. The encoding has nothing to do with the physical meaning of the state. The only purpose of encoding is to have an efficient realization. It has nothing to do with the specifications of the problem, except for that the cardinality matches and such thing. Except for that, there is no relation between them. Okay, so what you do is that we see you start with Q naught. That means you have not seen any of these patterns. Okay, then moment you see a 0, you are back. You are still in Q1. None of these, because see, both these patterns start with 1. You are with Q naught. Right. And what would be the corresponding output? Because C is otherwise, so the output will be C. Now that you have seen an 1, you have moved to Q1. So Q1 means you have already seen an 1. So you have moved to Q1. Right. So if you are currently in Q naught, you have seen an input of 1, you still output C, and you move to Q1 because you have seen an 1, and Q1 is you have already seen an. Now you have already seen an 1. Now there are two possibilities. Right. So either you can move to Q2, which is 1 0. You have seen 1 0, or you can move to Q3, which means you have seen 1 1. So naturally, you move to Q2 when the next input is 0, and you move to Q3 when the next input is 1. The output is still C. Right. Can you tell me what what happens next? So if you are in Q2, you have seen 1 0. If you are in Q3, you have seen 1 1. Now you have seen suppose the input is 1 again at Q2. What happens?
It's like 0, 1, so we are back at Q1.
You are back at Q1. You have seen 1. And if you are at Q3 and you have all right, so it's 1 0 1. If it's 1 0 0, then you are back at Q naught again because you have seen a 0. Okay, so you can think of like this. You can think of Q naught is that you have seen a 0. Is state the initial, and that's the initial state. Q1 is you have seen a 1. Q2 you have seen a 1 0. Q3 you have seen a 1 1. Okay, so now you need not have further states, because after this, if you have seen a 1, you are back to Q1 and you output A from Q2. If you have seen a 0, if you have seen a 0, you are back to Q naught and you output C. Similarly, from Q2, this was from Q2. From Q3, you have seen a 0, you output B. And then you have moved to Q2 because then you have already seen 1 0. Okay, so if you have fixed your states properly, then drawing this diagram is not difficult. It's just simple logic. You just decide of the pattern. Right. So this is the state transition diagram. Okay. The critical part is that deciding on your states properly. So here the states were seeing n 0 as q0, seeing n 1 as q1, seeing 1 0 as q2, and seeing 1 1 as q3. And by the way, can you tell me that why am I choosing 4 state? Why 4 state is necessary? Any crude idea why this is necessary? Depending on how much memory we have to keep. So it should depend on how much memory we need to detect this pattern. So you need to remember just two consecutions. Then you can find it. You don't need to remember further because this is a 3
So the
length.
last 2 digits.
Last 2 digits, only the
10.
last 2 digits in the stream you need to remember. Okay, so next is very simple. You have just converted this state transition diagram to the state transition table. And you have chosen this encoding for the input and output because you want to realize it using the binary circuits. So your Q not Q1, Q2, Q3, you have this 2-bit encoding. And similarly, A, B, C, also you have this 2-bit encoding. Right. Note that that there is kind of a okay. We'll come to this later when we go to that. There is a kind of don't care also. It's not just the output is ABC. There is kind of don't care also if we look at this encoding. Okay. So can anybody tell me? Or okay, we'll come to the D-flop realization later. D-flop realization in a more systematic way later. Let's take another example. Or let me come to this. Okay, so this is a circuit. Some circuit you have already designed. It's the serial ladder. Let me write down the. Okay, let's take some k-bit serial ladder. All right. So what we do? Let's take any. One. So you see, what are your inputs? You have 2 input. So the idea is like this. What we want to do is the following. Let's add this. Carry is 0. Initially also carry is 0. So let me have the input. And carry is 1. So you have 0. And carry is 1. So you have 1. Carry is 0. You have 1. Did I miss this? Yes. No. Yes. All right. So this is the Z. So what I want to do, I want to build a circuit like this. I have X and Y. Also, I have a clock. And I want a Z. And this sequence will look like this. So I'll have 0, 0, 1, 1, 0. 1, 0, 0, 1, 1. And the corresponding at every clock. So you know one of these comes at one clock, at the edge of a clock. So these 2 values comes at the edge of clocks. And then we get the output from the so I should write from the least significant bit side. Anyway, I'm writing it this way. Okay, so this comes at first clock, this comes at second clock, this comes at third clock, and so on. So this is what I want. So you tell me if you look at any point, if we just look at any point of this is the input, this is the input, and this should be the output, just one combinatorial circuit would do. Just one combinatorial circuit would do. If this carry was not there, suppose all these carries were 0, then we actually didn't need, we just had a combinatorial circuit. But since this carry is there, we have to remember, see each of these operations happens at one clock cycle. So this happens at first clock cycle, this happens at second clock cycle, this happens at third clock cycle, this operation happens at third clock cycle, and so on. So is it anything, is any output of the previous clock cycle that we need in the next clock cycle? Can anybody tell how many values from the previous clock cycle we need in the next clock cycle?
Sir, 1.
1. We only need the carry. You only need the carry. So this sequential circuit should have only one step memory. It needs only one step memory. If you just keep one step memory, that's enough. So basically what we will try to do is that, but anyway, there is a start state, there is a reset state or a start state. So we'll have two states anyway, because you are starting from somewhere. So just two states will be enough to represent the circuit. So can you draw the state transition diagram for this? Can you draw the state? So okay, so what does the states represent? So these states can, let me put the states as something, say Q. There are two states. Q is when carry is 0. Q naught is when carry is 0, and Q1 is when carry is 1. Because the memory can have two values. Memory can have two values. Okay, so now let me draw these two steps, Q0 and Q1. Right, and what are the inputs possible? Inputs can be either 0. So you have two inputs, X and Y. They can be 0, 0, they can be 0, 1, they can be 1, 0, they can be 1, 1. Right. Okay. So by the way, one thing I'm kind of ignoring is that I'm kind of ignoring the final carry. I'm just dropping the overflow carry here. I'm in this specification, I'm not bothered about that. So okay, so can you tell me the state transition diagram for this? Anybody of you? Just draw the state transition diagram. Initially, you know, there is, in the first step there is no carry. So initially I am at Q0. So what I will do is that moment I generate a carry of 1, I will go to Q1. And if the carry is back to again 0, I'll move back to Q0. I'll move back to Q0. Okay, so if the carry is 0, when can I move to carry equal to, sorry, when the carry is 0, that means I am in Q0. When can I move to carry equal to 1, that is Q1? What are the input conditions where I can move? Anybody? What is the input condition under which I move to Q1?
The XY is 1, 1.
Okay. So XY is 1, 1. What is the corresponding output I should have? What is the corresponding Z I should have?
Sir,
0.
0. Okay. So now that I am in Q1, what are the conditions under which carry can become 0 again? I already have 1. I already have carry equal to 1 here. What are the conditions under which it can move back to carry equal to 0?
0, 0.
0, 0. And what is the output? What is the output under
So
that
1.
condition? 1. Carry is 1, input is 0, 0, so output is 1. Okay. If I am in carry 0, under what condition I can stay back in carry 0? Carry can still be, I already have a carry of 0. For what input combinations I still have a carry of 0?
The remaining three inputs.
Remaining 3. So 0, 1 can be, what is the corresponding output? 1. If it is 1, 0, what is the corresponding output? 1. Why remaining 3? Which one is remaining? I am missing something. Am I missing something?
Sir, 0, 0.
0, 0. Yeah, if I am in Q0, I am back in Q0 if the input is 0, 0. What is the output? 0. What about 1, 1? 1, 1, I am transitioning to Q1. Okay, if I am in Q1, under any condition, can I stay back in Q1? What are the input combinations in which I stay back in Q1? Are there any input combinations? Are there any input combination for which I stay back in Q1? Yes or no? What about if carry is yes? What is the input combination? Carry is 1, and for what input combination carry is still 1?
So 0, 1, 1, 0,
Exactly.
and 1,
Very
1.
good. Very good. 0, 1. I'm writing output. 1, 0. Write the output and 1. What is the output for 0, 1 and carry 1? 0.
Sir, 0.
1, 1, carry 1, 1. 1, 0, carry 1, again 0. Okay. So you see now all conditions are taken care of. All conditions are taken care of. Okay. Actually, there is an easy way to check. You see there are 8 edges in this graph. There are 8 edges in this graph, and you have X, Y, and carry. So there are 8 combinations possible, and so all these combinations are taken care of. Right. So this is the state transition diagram. Now let us look at the corresponding state transition table. Let me go back to the slides that it's already done. Okay, so there is already done. So here is the state transition table. So if your present state, which is carry 0 or carry 1, is the following, your next state can be either carry 0 or carry 1 depending on your inputs. So it's either 0, 0, 0, 1, 1, 0 or 1, 1. Okay. So if your input is 0, 0, if your present state is carry 0, you stay in carry 0. If present state is 1, you still stay in carry 0. Your input is 0, 1. If you are currently in carry 0, you stay in carry 0. You are carry 1, you stay in carry 1. Similarly for 1, 0. For 1, 1, if you are in carry 0, you move to carry 1. If you are in carry 1, you are still in carry 1. And these are corresponding outputs. Okay, actually here I have, sorry, it's slightly, this specification is slightly different from the specification that we had drawn. Here, your output is not only the sum, it is also the carry. It's also the carry. In fact, you need that. If you have a serial adder, you will need to write the carry. Okay, so there are the output delta is SI as well as CI. SI as well as CI. So 0, 0, 0, 1, 1, 0, 1, 1. Okay. So accordingly, I have so this what will be the so I have in my specification, I have in this diagram, in the state transition diagram that we have drawn, we have only given the SI. Here also the CI is mentioned. here also, but that's easy. That's easy to decide what the CI will be, what the CI will be. And we have kind of the encoding. I think you are all clear. The output encoding is this. CI is the output encoding, and Q0, Q1 is just the value of carry. That's the input. That's the state encoding. Okay. So now let us see. So if you permit, we are through the second step. That means given a specification, we could with a proper state assignment and state encoding, we could come and also the output encoding, we could come up with a state transition diagram, and we could come up with the equivalent state transition table. The next step is to realize this state transition diagram. Now, let us say that we decide that we will realize using usual gates and a D flip-flop as my memory element, Okay, so now let us see how to do that. I'll come back to this state transition table, but now let's see. So, by the way, one thing you observe that okay, let me go, I'll do this later. Let me go back to that. Okay, so by the way, this is a milli machine because output depends not only on the inputs X and Y, but also the state, which is the carry in this case. So output depends on that. So it's a milli machine. Here is my combinatorial cloud. Combinational cloud. And here are my primary inputs, X and Y. Here is my primary output, Z1, Z2, which actually is SI and I have a clock. Okay, sorry, the clock is not here. It's a combinatorial circuit, and I realize it using D flip-flops. Okay, so this is a milli machine. Okay, so let me see what happens. What is happening? So this xi yi as well as something called a state, which I denote by y, will determine my z. Okay, and as well, it will determine the next y. So the value of y, which is representing the state, I call it as an excitation input. So I don't call it a state, actually I call it an excitation input. Okay, and this excitation input is generated by my memory component. The memory component takes the current state and generates the next excitation input. So so I have said that this memory component will be using flip-flops. So depending on how much memory you need or what are the number of states that will you have, you have to decide the number of flip-flops. So if there are two states, Q0 and Q1, how many flip-flops should you need? One flip-flop would be enough. So this would be just a single flip-flop, rather one single D flip-flop, let's say. And the property of D flip-flop, you know that at every clock cycle, whatever is the input D, that goes to the output Q. Whatever is input D goes to the output Q. Okay. So this is fine with everybody. So can you tell me what does Q represent in our case for a given D? What does Q represent? What is D and what is Q in our case? Anybody?
So carry out and carry in.
Right. It's carry in and carry out. D is carry in, Q is carry out. Okay. So which we have denoted as our states. All right. So now what we will do is that we will form a state transition table, which is like this. We will have the present state. And then we'll have different inputs, which is xi, yi, different values of inputs, say 0, 0, 0, 1, 1, 0, 1, 1, xi, yi, like this. And then we will have the next state and the output. So can you tell me, so it is still the next state, but in this my different nomenclature or different nomenclature which helps my realization using a D flip-flop, this new state is nothing but the excitation, new excitation Y. And this present state is also the old excitation Y. In this case, it happens to be the carry in and carry out, and you have the output. Okay. So what I do is that, so this is fine. This is same as the state transition table that you drew earlier. Any doubt regarding this? Okay. So now what we will do, I'll separate out this column from this column, and I'll draw actually a larger, a slightly isolated table. So I have my present state. And I have my inputs. I have defined combinations of inputs. And I have two present states, which is 0 and 1. And this part will represent the Z, which is SI, CI, and this part will represent the, it's usually the other way around. So it's usually the output Z, SI, CI, which is SI, CI, and this is the next state. Okay, so can you fill up this table? If the present state is 0, okay, you don't need to fill up. Let me come to the slides. Let me fill up this table. So this is the table, except for the fact that I have separated this out, and I have replaced this new state by something called an excitation, which is nothing but the Q value of the D flip-flop, which I am using in the memory part. Now you look at one thing. You just look at any one of this column. Let's say the NS column or the excitation column. You look at this. So if you interchange these two columns, 0, 1 and 1, 0, if we interchange these two columns, then I think I should have drawn it there itself. Okay, but anyway, you kind of blank out this this O columns. You just look at this NS column, and if you interchange these two these two rows, these two columns, then you see this is nothing like but a Carnot map, isn't it? It is nothing like it is just a Carnot map. And what are the on set of the Carnot map? If you just look at NS, I'm trying to first build the combinatorial circuit for NS. Okay, what is the on part? This is on part. This is one on. This is one on, and these are two ons. These are two ons. Okay, you forget the O column actually. I'm not copying the. I'm being a bit lazy. I should have copied this table there, but you can maybe visualize. You can forget the O column. You see this, and if you interchange these two columns, which is the gray code format, you see this is nothing but a Carnot map. This is nothing but a Carnot map. Okay, and if this is a Carnot map, similarly you can have Carnot maps for the first bit of O as well as the second bit of O. You can so you can build three different Carnot maps, three variable Carnot maps from this state transition table. Okay. And all of you know that once a Carnot map is there, it's easy. You can easily find out the combinatorial circuit for that. So what you do using this Carnot map, you come up with the combinatorial circuit, and that you have here. So you actually have three different combinatorial circuits here. One for, you have two different combinatorial circuits. Three different combinatorial circuits. One for SI, one for CI, and one for Y, the excitation. Okay, three different combinatorial, so that will constitute your combinatorial cloud. Okay, so I will ask you to solve one more exercise. It's a typical problem that we encounter in any automata, is a pattern finding circuit. A pattern finding circuit or a pattern finding sequential machine. So what it is supposed to do, you get only one string as input. You only get zeros and ones as input, only one bit. And depending on the value of the bit, whether it's 0, 0 or 1, 1, you give a certain output. There can be other forms also. There can be simpler forms of this. For example, you are getting an input stream of ones and zeros. Whenever a certain pattern comes, let's say whenever 0, 1, 1, 0 comes, you have to, the output should be 1. In all other case, the output should be 0. So you have delta to be 1 or 0. This is a slightly more complicated case. You have three different delta for different input patterns. Three different input patterns. Okay, so I would like you to solve this problem. And maybe in the next class we will ask you to give a solution for this, to submit a solution for this, which you have to follow these three steps. You have to define the states, you have to draw the state transition diagram, you have to do an state assignment or encoding, you have to draw the state transition table. From there, you have to do a D flip-flop realization using the excitation table and a Carnot map realization of the excitation table. Okay, thank you. With this I end. If you have any question, you can ask. So we are not meeting in today's lab. We are not meeting in